So can you see my screen?
Yes, sir.
Okay, thank you very much for confirming, and thank you very much for the introduction. So uh, welcome you all. First of all, I would like to thank you know Modern College of Engineering and also AICT for conducting this FDP program. And that as so today my session will be mainly focusing on designing and analysis of permanent magnet synchronous motor for traction application. Why I have chosen this topic is basically, as we know, the e-mobility is today a buzzword, right? So you see, like electrical vehicle is a buzzword, and day by day, we are getting new vehicle into the market. So it's basically like we have a lot of opportunities in this particular domain. And when we speak about e-vehicle, motor plays an important role, because in place of engine we have electrical motor we drive, and the battery system. So it's electrical designing of electrical motors is very important, and there is a complete paradigm shift in the designing of electrical rotating machines. And you are going to see in my presentations how the industry is practicing those best methodologies, and I'm going to showcase. Let me start with the agenda. So in my presentation, basically, if you see, this is I will start with the introduction of Altair and Altair e-mobility solutions. So, and first I will talk about the e-motor challenges. So first, before designing any product, we need to understand what are all the challenges that we have in the designing of a motor which goes into electrical vehicle application. Then we will talk about Altair global workflow to address these challenges. So in which I will be showcasing you how to set up the model for the PMSM mission. So we'll also talk about the state of art analytical computation, basically the equations that are used to compute the sizing or the structural data of the motor. And as I said, we will see how to set up the model. So live demonstration I will do, and we will see some case studies, best practices from the industry. So we will also discuss about the thermal and the noise levels that are coming out from the motor, and then we will see the optimization cases. Then I will summarize, and then we will take up the question and answer session. So this is my agenda. Let us start introducing the Altair. Altair is basically a simulation technology company, and it was founded in 1985, and we have 86 offices in 25 countries with 3000 plus engineers, scientists, and creative thinkers. And globally, we have the 8000 plus customers. And that was about the introduction about Altair. And as you see, technology evolution is happening, right? So it is happening in many domains. So if you look at it is happening in Internet of Things, and machine learning, cloud computing, additive manufacturing, and also the smart products. And last but not the least is basically e-mobility. When we say e-mobility, the definition is basically converting fuel-driven powertrain into basically electrically powered powertrain. So when we do this, the system, basically the systems or subsystems that we are going to have in the electrical vehicle is going to become a very complex. And at the same time, we need a new methods, and also we need a new technologies to innovate and design these subsystems. And at the same time, the transportation OEMs, okay, real equipment manufacturers need sustainable technologies to meet the demands. There are also demands coming from the customers. Okay, so what are all those demands? So whatever we design, it has to be a safer, and it has to be a lighter, it has to be a greener, and it has to be a smarter. So that is what the demands that we get it from the customer. So we need to meet this, as a designer, we need to meet these these demands and design our products. So electrification, just going back, electrification is not only limited to cars, but when we say, most of the times when we say electrification, there is a perception that it is happening in only cars, but it's not only happening in the cars, it's happening in a two-wheeler and three-wheeler. So it's happening in the buses, trucks, and also off-road vehicles, and also the autonomous operation vehicles. So so for all these vehicles, Altair as a simulation technology company, we can address several physics or several domains. So we can help in designing electric power, electric drivetrain, and we can also do the safety, durability, NVH, and lightweighting simulations. And And then we can also do the sensor and communications analysis and electromagnetic compatibility for EMI/EMC studies. And then like we can also do the energy management. That means basically complete system level simulations we can perform. And then we can do the optimization. So when I say optimization, it can be a topology optimization. 1 minute, I'm not sure. Okay, so it's for a topology optimization. And then we can also do the vehicle dynamics, basically solving the kinematics of the vehicles. So these are all the domains which we can address at Altair. And these are the solver technology, as you can see, to address those particular domains. So if you see here on the top, we have a software basically called Radios. So we have a software called Radios. Basically, it is basically to do the crash, safety, blast, and also gravity. So it's basically used to do the structural explicit analysis. And then we have OptiStruct. OptiStruct is basically to do the durability and vibration, acoustics, and buckling and heat transfer analysis. So it's basically structural implicit analysis tool. And we also have casting tools, basically we call it as a manufacturing tool. So it's basically to use forming, extrusion, and additive casting and also modeling. And on the top of this, we also have a 1D simulation tool, math-based tool. So we have Activate, and then we have Accusol, and Accusol is basically to do the thermal simulations. And then we have a motion solve. Motion solve is to do the multi-body dynamics and kinematic equation solving. And then for the electromagnetics, we have two simulation technologies. You can see it's basically FICO and Flex. FICO is a high frequency tool, and Flex is a low frequency electromagnetic simulation technology catering to electrical engineering. And on the top of this, we also have optimization tool called HyperStudy, so which basically does the DOE, design of experiments, and also the optimization studies. So it will the HyperStudy will link with all these solvers, which basically to do the optimization. And I basically come from electromagnetics background, and that too electrical background, and that too my expertise in low frequency electromagnetic tool. And in fact, motor is also electromechanical component. And we use Flux, which is a general purpose finite element based electromagnetic and thermal simulation technologies to design the motors. And it is there in the market from 35 years, and it helps the engineer to innovate and design an energy efficient component. And this tool is based on Maxwell's equation. So Maxwell has written a 4 partial differential equation, so relating magnetic and electric fields. So we apply some numerical methods to unlock the magic of Maxwell's equation. And we also use the the material characterization equations to relate fields, and also electric and magnetic fields, and we solve the problem. So these are the main applications which we can simulate by using low frequency electromagnetic simulation technology, Flex. And what we can do, so we can simulate the motors, and we can also simulate the generators. Then we can do the transformers and inductance. We can also do the sensors. As you can see here, there is a wheel, which is there is a wheel, and there is a sensor placed nearer to the wheel. And as the wheel is rotating, there is change in the reluctance path, as you can see, because of which the magnetic field is varying. So these kind of simulations we can do. And on the top of this, we can, motor is basically providing the motion in rotating direction. So we also have actuator which provides the motion in linear direction, so motion along one axis. So this kind of these kind of actuators we can simulate. And we have in Flux, basically we can compute the closing time, opening time, and we can compute the saturation. So saturation is nothing but flux density distribution. We can compute the eddy currents, and we can also see what is the force on the moving part once you apply the current to the coil. And then we can do electric field calculations. And the low frequency tool is capable of doing thermal simulations also, because of which we can also do the induction heating. So heating up the device by pumping the eddy current. So it's a contactless heating. And then we can also do the wireless chargers, so which is basically for the electric the electric vehicle application. So it's like a transformer only. So we have a primary and we have a secondary. And we pump the current to the primary, and because of mutual induction principle, there is a flow of current in the secondary through the converter basically connected to the battery, and because of which we convert that signal to DC, and then we store it in the battery. And we can also do the EMC simulations, as you can see. So there is a car body, and the car body is modeled with a shell element, and on the top of the car body we have a cable which is carrying some amount of current. And as we know, the source of the magnetic field is flow of current. So there is a flow of current and we have a magnetic field, so we can see the magnetic field around the cable and along the width of the car body. And then we can also simulate the power cables. You can see here the power cables, 3-phase power cables. When we pump some current, and we can compute the Joule losses, and also we can compute the temperature distribution and the flux density distribution. And there are also some special applications which we can simulate, ship magnetic signatures, and we can simulate the bus bars and the power modules. So these are the main applications which we can simulate by using our low frequency electromagnetic technology, flux, which basically cater to the electrical engineering. So coming to the e-mobility, so these are the applications. As you can see, we can simulate the traction motors, and we can simulate the alternators, especially for the rigidity braking system. And then we can simulate the stators, and as I said, wireless chargers, and position sensors, especially position sensor, so to define what will be the optimum distance between the target and sensor. And we can simulate the speed sensor and torque sensor to measure the torque, and actuator to provide the linear motion, and we can simulate the electric power connections. So that was an introduction about the Altair and the Altair simulation technology, and also the low frequency electromagnetic technology, which is catering to the the electrical engineering. So coming to the today's topic. Today's topic, basically designing and analysis of motor using the simulation technology called flux motor and flux. We will see. So before going there, first thing is we need to understand what are all the challenges that we have when we design a motor for EV application. Let me start with this slide. So as we know, and we are designing the motor from the ages, right? So I must say, motor is a complex piece of a machine with a stringent performance requirement. When I say this statement, basically why I say this statement is, so if you look at let me explain by considering two examples. Okay, so one is a motor which goes into industrial application, and another motor which goes into the EV application. Okay, so when we say in the industrial motor, most of the time it will be operating at one single RPM. And as a designer, we need to target all the performance characteristics for that particular RPM only. It can be efficiency, or it can be a losses, or it can be anything. It can be a cogging torque, or it can be a back EMF, anything. But basically, we will be targeting, keeping in mind that particular RPM. But if you look at the motor which goes into electrical vehicle application, it's not single RPM, it's a multiple RPMs, right? So multiple load points. So what I'm trying to say is we need to target the several load points, for which we need to maximize the efficiency throughout the duty cycle. Duty cycle is nothing but basically it's a load points, or it's a load cycle. So in India, normally we use NDEC. So NDEC, New European Duty Cycle, or WLTP duty cycle. So we need to maximize the efficiency for full duty cycle, or it can be any duty cycle. So duty cycle depends on the vehicle also, and so it's not a single RPM. So that is one constraint. So, and it's not a single physics, it's a multi-physics. Okay, so when I say multi-physics, let me explain this. So if you look at the industrial motor, most of the times we have no limitation on the space. If you look at the motor which goes into the which is placed at the shaft floor, we do not have a limitation on the space. We have an ample amount of space to fit that particular motor. But if you look at the electrical vehicle, we have a limitation on the space. The guy who decides the load locus, he will tell this much space is available for you, and you have to target your design in an available space only. So that means we have a limitation on the space. When we have a limitation on the space, we will not have an ample amount of space to dissipate the heat. So because of which, if the heat dissipation will not happen properly, and we will have a thermal issues. So that is one constraint. And also, if you look at the industrial motor, we are not bothered about the noise made by the the motor which is there at the shaft floor. Sometimes it's in the industry, the motor noise is required, but when it comes to electrical vehicle, the noise we need to reduce it, because the noise that comes from engine is, the noise that comes from motor is completely different. The noise, basically the quality of noise for coming from the motor is not good noise. It's not a good quality of noise. It's annoying noise. The guy who is sitting in the car or who is riding the two-wheeler, like he will not feel comfortable. So that's why the reason there are also some standards coming in to reduce the noise. And at the same time, we need to reduce the weight. Weight is also concern for us. Okay, and at the same, by keeping all these things in mind, we need to target the good performance of the machine. And what I want to conclude in a nutshell is basically, like, it's a multi-physics design where we need to balance the noise, thermal constraints, and also like weight and also the performance. And then on the top of that, cost is also concerned, because most of the motors which goes into electrical vehicle applications are permanent magnet motors, and the cost of the motor is directly proportional to the cost of the permanent magnet. And in India, like, we do not have the resources of a permanent magnets. We need to import it, and it's also, it's a minimum magnet. The minimum magnets, we need to get a higher torque density and also the power density. So we need to keep that in mind. And on the top of that, we also have we also have controls in place, right? So when we have controls in place, we have a power electronics, and power electronics will send high frequency signals into the motor, which will create a noise for me. So that is also one challenge. And time to market is also important. So as I said in the opening of my presentation, if today, like, every day, like, we see one vehicle. So if you're not bringing your component quickly into the market, the consequences. So that's why the reason, what I say is keeping all these challenges in the mind, and also, like, we need to bring the product quickly into the market. So what I propose is, we need a new methodologies, and we need tools to quickly simulate or virtually simulate this particular constraints, and also we need optimization methods to to design or to address the multi-physics problems of electrical rotating machines. So that was the challenges on the global level. And also, like, let us look at the challenges that we have on the design, from the designer point of view. So the guy who decides, who designs the motor, basically he will get this, the specifications which is shown at the bottom of this presentation. So he will get this kind of specifications, like saying maximum torque rating and maximum power and motor speed and also motor weight. So once he get the specifications, he need to start the design. So what are all the things he need to keep in mind? So first thing is, like, he need to look at, like, what are the, what is the space available for me, and he need to accordingly target the machine dimensions. And then he need to look at the open circuit tests. So basically to compute the back EMF. So the minimum voltage that we need to pump to the motor. Anything beyond the minimum voltage will be converted into the useful mechanical energy. And then the performance envelope that we need to target, and the cooling arrangement that we need to use to cool the motor, and then the power and torque density that I need to target, and the cost and warranty definition that I need to provide for my motor, and the manufacturing technologies that I need to use. So you cannot design a motor which is not manufacturable at a shaft floor. So you need to keep that first in mind, and then start the design. And integration with the motor controls and CAN bus, which makes the the system very complex. And on the top of motor, we also have a system which is basically a transmission and a vehicle chassis. And to control the motor, we have a software. So there are hundreds of codes of C code which is there, which goes on the top of the controller, which is basically used to control the motor. So, and when we have a controller, as I said, like, we have a high frequency signals which makes the whine noise, which also makes the motor very complex. So that is what, like, as a designer, he need to keep these things, these points, some of the points in mind, and start the design. And what is EV motors? What is unique to India? Okay, so what is unique to India? So we need to keep in mind, like, what are all the driving speeds that we need to target. So if you consider, like, if you consider, like, highways, like, we can go up to sub 40 kilometers per hour, or like sub 50 kilometers per hour. Or like, if you consider the district roads, we can go up to sub 30, or like sub 35 kilometers per hour. And the driving habits, so it is basically taken in a way that, like, most of the times we have indisciplined driving habits. And the loads, basically, like, we always try to put more loads basically and then the roads. So it has been considered in such a way that, like, the roads with potholes, and the efficiency. By considering all these things, like, the efficiency that we need to target, so we need to keep in that mind. So what I propose is, like, it's better to test the motor. Once you design the motor, test it with a duty cycle. So it's, you can see here there are two duty cycles. One is the new European driving cycle, which is coming from theoretical data. So it's a duty cycle is nothing but it's a three-dimension data, where, like, in one dimension we'll have a time, in another dimension we will have a torque, and in another dimension we will have a speed. So that is what, like, we have. So this data basically for NEDC, like, it's a theoretical driving cycle. But yes, like a new DT cycle, I think, like, Indian government is also going to adopt WLTP for the the electrical vehicle. So this WLTP coming from real test data. So you can see here it's coming from the real test data, and it's better when we design a motor. It's also better to test it with a WLTP. So this is what, like, I propose. And on the top of that, we also have a standards coming from IC, and also, like, standards coming from NEMA. So it's always recommended to have, like, higher efficiency. I have a customer who designs the motor, basically it is basically ranging from, like, 95 to 97% of efficiency. And these are the standards which we need to keep in mind while designing the motors. Okay, so we have seen the challenges, so global level challenges, and we have seen what is the challenges from the designer perspective, what is unique to India when it comes to electrical rotating machines, and what are all the duty cycle we need to adapt for the designing of electrical motors. And let us say how Altair plays an important role in addressing these challenges. So if you see here, Altair proposes a global workflow for the designing of electrical rotating machines. It goes from the concept phase and to detailed stage, and then the system integration. So once we get the design specifications from the guy who decides the load locus, so we will have what is a torque rating that I need to target, and what is the space that is available for me, and what is the current that is available from the battery. So I know those things, and then I need to start the design. So first we will try to first what we will do is, like, in the concept phase, we will quickly try to do the rapid design of exploration to target the design by considering all this data from the load from the guy who decides the load locus. And we will quickly select the the stator topology, rotor topology, winding configuration to target the design. And then this is basically semi-analytical calculation, semi-finite element calculations we will do here to quickly target the design. And then we will go to the detailed design, where we will do the the finite element calculations. Once we design the motor, we will freeze the design in the detailed stage with the finite element calculations, and the finite element calculations will be more nearer to the practical results. And then once we freeze this, then we will integrate that particular motor into system. So motor is a single component, but how this motor will behave when we connect into the system, so that we will do by integrating into the system. So this is what we follow at Altair to for the designing of electrical rotating machines, and this is what we propose to our customers also. So as I said, so what we will be doing, so first concept phase, you can see here we will be using a flux motor and hyper study, so which I have mentioned. So these are the simulation technologies to do the to quickly target the design. And in the detailed stage, we will do the we will do the electromagnetic, structural, and thermal simulations and responses. You can see here power, torque, and torque ripple, and maximum speed, losses, and temperature, and demagnetization. And also we will do the stress analysis in the detailed stage. So this is in the detailed stage, we will have finite element calculations. Then we will have a system integration. So we will have all the other subsystems in place, and we will do the full duty cycle simulations. And also on the top of that, we can also do the system optimization by considering the WLTP as a duty cycle. So this is what we do. And what are all the tools? So just to recap, what are all the set of tools that we will use to do this kind of analysis? At the concept phase, we will be using flux motor and hyper study. So down the line, I will be using these names. I will pause here just to digest these names, so that there will be no confusion. So at the concept phase, we will be using the flux motor and hyper study, and in the detailed stage, we have a flux and OptiStruct and AccuSolve hyper study. So to do the electromagnetic, structural, and CFD simulations, that is a thermal simulation. And then we will use flux and activate to do the system level simulation. So once we do this, so these are the set of softwares that we will use to designing of electrical rotating machines addressing the multi-physics. Let me also walk you through, how, the pre-designing of e-motors, like, quickly targeting the design, what are all the state-of-art analytical equations that we use. And if you look at, before starting the design, we need a first numbers, right? The length and breadth of the motor, the rotor dimensions, stator dimensions, number of turns, and also like the pole and slot combinations, all those things. So how we select those things? So if you see here, so these are the state-of-art analytical equations targeted for permanent magnet machine. And at the first, so we need to fix the values of following parameters, as you can see on the left side. So we need to assume the first, permanent flux, remnant flux density of a magnet, and maximum stator yoke, and maximum rotor yoke, air gap flux density, and air gap width, and winding length, end winding length. And then you can see on the right side there are certain analytical equations which we can use to target the, the stator inner diameter, rotor yoke length, stator yoke width, and rotor slot length, and also stator outer diameter, and the magnet dimensions. So once we get this, then we need to select the poles and number of poles and slots, right? So how we can choose the, the number of poles and number of slots. So to do that, I have put some points here. So basically, while choosing poles and slots, so we need to keep this in mind and try to select the, the poles and slots. So to increase the number of poles, increase the number of poles to increase the torque density. So if you increase the number of poles, the torque density of the machine will be increasing. And target the slot filling factor between 0.4 to 0.6. So because we cannot go beyond that. We can go, but there are some technologies where we are going for higher slot filling factor. But yes, so the minimum values is basically 0.4 to 0.6, and because we have a slot liners, impregnation, and also the insulation. And then obtain the winding factor as close as the 1, so that you have a better performance, and you have a less harmonic content. And the cogging torque, you have to limit it. So cogging torque is nothing but a detent torque, or no current torque, so which is unwanted phenomena in the permanent magnet machines. So we need to reduce it, because cogging torque again will induce the torque ripple. So once you have a torque ripple, it will have a noise and vibration problem. So we need to limit the cogging torque. And then maximize as much as possible the current density to avoid the overheating of the motor. So we can minimize the current density, but yes, to reach a higher performance of the machine, so sometimes we also required a higher current density to be placed in the windings. So especially for the the hairpin type winding for the the permanent magnet machines, where the current density is high. So if you have a better coolant methods to cool your motor, then we can have a higher current density. But yes, if you don't want to use the the current density, then I would recommend you to just to minimize the current density to avoid the overheating of the motor, and optimize the saliency to increase the capability to reach a higher speeds. That is basically talking about the field weakening region to reach a higher RPM. So, and that was about the guidelines to choose some guidelines to choose the number of poles and number of slots, and the choice of rotor. So if you see here, I have selected 3 the rotor topology. And if you look at the rotor topology, there are 3 basically magnets which are placed on the surface of the rotor, and inserted inside the rotor, and also buried inside the rotor. So I have compared several performance parameters on the the left side, and for the surface magnet. So if you look at all this performance, so buried magnets will have several advantages on the torque to weight ratio, and high speed running possibilities, and also the power factor, and also the efficiency. The cost, it depends basically. So it's better to the manufacturing cost to buried magnets is increasing. So that is what. And also surface magnets are more easy to industrialize. That's what I say. And this is what on the topology selections of the magnets on the surface of the permanent magnets. And then choosing of winding configuration. So here I have compared the concentrated winding and the concentrated double layer winding, and no overlap. Basically, like one particular phase going into the slot, and overlap is basically like two particular phases are going into the one slot. And you can see here. So I have compared on the right side fundamental winding factor, and which is having.
Excuse me, sir. Excuse me.
Yes.
1 minute. Trupti madam, please switch off your camera. Please take care that the camera should not be on. Trupti madam. Trupti madam. Okay, sir, continue.
No worries. Thank you. So if you look at this winding configuration, I must say no overlap will have a fundamental winding, good winding, fundamental winding factor, and the concentrated winding will have the back EMF shape is basically trapezoidal, and for all other windings, like we have a sinusoidal shape of winding. And for slot filling factor, so we will have a good advantage. So slot filling factor is very important one. So with no overlap and concentrated winding, we'll have good advantage when compared to the concentrated double layer and also the overlap winding. So this is what the comparison of the four types of windings, and so from this, like, we can make out like which type of winding is suitable for my application. And then coming to the motor comparison, so I have compared three major motors which is normally used for electrical vehicle application, which I see in the market is a PMSM, so permanent magnet synchronous motor, and the induction motor, and the switch reluctance motor. So if you look at, I have compared several parameters for these three kinds of motor. So first one is power, power and torque density. So I must say PMSM motor will have a good advantage when compared to induction and SRM motor. And then, like, on the efficiency side, again, PMSM will have a good advantage. And then the torque ripple is, SRM, it's because of the shape, the topology effect. You can see, it will have more torque ripple, which is unwanted phenomena. So which will induce the, the noise into the noise noise. On the noise side, like you can see, again, as the torque ripple increases, like, noise will increase. So SRM motor will have more noise. And the motor cost, if you look at, like, a permanent magnet synchronous motor is on the higher side. So because, like, we have a permanent magnet, so so that's why the reason, like, the PMSM is more costlier than when compared to induction and also the SRM motor. And control cost, the controlling side, basically SRM is it's very difficult to control. So as we know. And fault tolerance, I say PMSM is poor, and induction motor and SRM is excellent. So why the reason why I say poor is, in the PMSM motor we have a permanent magnets. Permanent magnets are sensitive to the temperature. So, and we have sometimes a problem of demagnetization, because of which the torque level will come down. So that's why the reason, like, I say PMSM is poor. And the winding location, so it's on the PMSM, like we have on the stator, and induction basically stator and rotor, and SRM we have it on the stator. So, and reliability side, induction and SRM is almost the same, so when compared to PMSM. So this is what, like, the comparison of the motors, especially like the motors which goes into electrical vehicle application. Now coming to the setting. So with this idea, like, so whatever the equations that I have given, like, the challenges with these ideas, like, we can quickly target the design. So for that, like, we have a flux motor as a technology, as I said. So it's a straightforward workflow. A machine can be designed within a minute. So there are three main steps in the designing of electrical rotating machines. First is design, where we will design the motor starting from the stator to rotor, and we quickly perform the test and we generate the report. So what I will do is, like, I will try to open the software. We will try to set up one or two, the cases, load cases, that is for the cogging torque and back EMF. Then we will also see some results on the motor. So let me open the software. So So this is called a flux motor. So it's a multi-physics platform, and where you can quickly design the electrical rotating machines. And I would like to open, so it is available. So it's available for the permanent magnet synchronous machine inner and outer rotor and induction motor. So let me open one example. Ma'am, can you able to see my screen just to confirm? Hello?
Yes, we can
Yes.
see.
Okay, ma'am. Okay, so we will look at, we will try to set up one model, how exactly it works. So this is how it looks like. And this is the, this is a motor factory environment. As I said, like, there are 3 steps to do. One is a design, test, and also like, the export. So first is the design. So where we will be designing the motor step by step. And in the design first, so from the analytical calculations, we can compute all the the structural data. So I already have it, and I will be trying to enter those structural data into the into the software. And it's basically for a 50 kilowatt machine, 400 Newton meter torque requirements. So let us try to enter those dimensions. So first one is a topology. I'll go to the topology. So you can see here there are several topologies available, like okay, so it's basically first one is like, it's a rotor outer diameter is the resulting one. So so we need to enter the stator dimensions and rotor dimensions, and outer diameter will be the resulting one. So second one is the air gap length is a resulting one. So we need to enter a stator dimensions and also the rotor dimensions, and the air gap length will be the resulting one. Let me choose that one first, and let me try to enter those numbers. So it's first 269. 269, so 161.93, and then like I will, so graphically you can also see, like, whatever I'm trying to enter, graphically it will tell you like what I'm trying to enter. So just try to correlate what I'm trying to enter, entering into the tool. So it's a length, and then like a number of slots. So it's 48 slot machine, and then similarly, I need to enter the values for the rotor. So it's 160.42, and then the inner diameter is 111, and then we have the length, so which is around 83.1. So I just need to correct this one, 83.1. So then it's a 8-pole machine. So I just click, and it will size accordingly, and I have entered the structural data, that is a topology. Then quickly, like, we will go to the magnets. Okay, so we will try to select the magnet shape. So if you can see here, so I have gone, so we have a magnets on the rotor. So I have I have selected the magnets, and you can go here, and you can see there are several magnet shapes available. Standard magnet shapes are available here. So whichever the magnet suits for your application, you can select. And here I will select the magnet shape, the V-shaped magnet, so which is buried inside the rotor. So in which I will select this one, V block. Okay, 1 minute. So okay, so this magnet I will select. So IMI V block 01A. So this it's just a name, so there is no meaning for it. So just I will select that one. And this is the the magnet which I have selected. So I need to give the the structural data for this magnet. So I'll give the structural data. So 6.5. So you can see graphically like what I am trying to enter. 9, and the T1 is 10. And then like T2 is 1.4. And 5 and 0. So I have entered the magnet dimensions, as you can see here. As you can see here, it has changed the shape, and I have a V-shaped magnet which is buried inside the rotor. And then like once you do this, like we need to orient the magnet, so the polarization, so the guy who supplies the magnets, he will supply just a ceramics. Okay, so once you get those ceramics, like we need to orient by using the magnetizer. So normally, like there are several ways to magnetize the magnet. So it's if you can see here, so it can be radial or it can be parallel. So it's it can also be by we can also do it by orthogonal. So here I will select the parallel orientation. So here I will, so to do the parallel orientation, I need to select the direction. So, and the angle is 90 degrees. And once you once you are done with the rotor, so we need to shift to the stator. So stator first is the slots, and I can select the slots. So these are the slots shapes, standard slot shapes are available, you can see. So if you want to bring your own shapes of the slots or magnets, you can also do that. And so for example, like let me select OS free, and then like we can select OS free 3A. Okay, let me go down. So this one I will select, and I'll try to bring it into the motor factory. So I'll click OK. So see here, I bought the slot shape. So I just need to enter the structural data, and then like we can do the simulation. 9 and 2. So these, so you can see graphically, like whatever I am trying to enter, all it's graphically it's shown in the graphical zone. .9 and then 1.93. So I try to validate this. So I am done with the slots, and now like we can shift to the winding. And the winding, so you can see here there are several tabs here. Winding first, like I want to go with a star, and I want to put, so flux. This tool will allow you like 4 levels of the winding the winding modes. Okay, so each level have a certain degree of freedom. Okay, so I will put automatic, so where like I need to define the number of the parallel paths and phase sequence, and I can do that. So let me so this one is a number of 1 minute. So let it be 1. So I will go to the coils, and then like I'll try to select the table. So tables, like the wire gauge table. So if you look at, like there are 2 tables available for the wires. So it's American wire gauge table, and also like we have a metric wire gauge tables. So I'll switch to our American wire gauge, and I can select the 19th one here. So I'll just select this one, and I can put number of coils per number of turns per coil, so which is 9. And then like we can select the number of turns, so in hand, so it's a 13. So I'll just validate this, and then I can also define the the end winding dimensions. You can see here. The first thing is like end winding topology. So what kind of topology we have? So it's a U shape, or like it's a C shape. So there is also Y shape, and let us consider your U shape, and I will just try to select the give the dimensions on the connected side and the non-connected side. So it's 35, and then it's 45 and 45. So click OK. So I've set. So this is what like I will validate this. So this is how you can set the winding configurations. You can also see the winding layout. So you can have this is a winding layout, and then like you can have a radial view and also like you can have an axial view. And so then we can assign the material properties quickly. So to all the components which are there in the motor. So first one I would like to assign is for the rotor. So rotor magnets, let me select so let me select it's basically like NDFEB magnets. So just 1 second, I just need to recall the name of that magnet. So it's basically it's NDFEB magnet. So let me pull. Okay, so 1200, this one to 1230, and also like 1400 magnet, and then the the magnetic circuit is M270-35A. So which means like this particular steel has a 2.7 watt loss per kg, and the thickness of the lamination is 0.35 mm. So that is what I have chosen. So similarly, like the coil will be the copper, and I will choose this one, the same material. So for stator and rotor has the same material. So that's I can choose M270-35A. And once I'll validate this, so I'm done with the materials, and we can go to the test. Okay, so quickly, like you can also do the several kind of tests. So you can see here, first one is open circuit test. We can in the open circuit test, there are two tests available. One is a cogging torque and back EMF. So let me do the cogging torque test. So when you do the cogging torque test, tool will tell you what are all the settings that we need to do, and what are all the inputs that is required to do the cogging torque, and what is the outputs that you will get it. So as I said, like first thing is we need to set the temperature. For this, like to do the cogging torque set, like test, like we need to set the temperature. So I set 80 degrees as a temperature, and I will try to run the model, and then I'll go to the back EMF. So let it run. So it will take some time to run the model. So in the back EMF is basically, if you look at like to do the back EMF test, what are all the settings that we need to do, and what is the inputs required, and what are all the outputs that you can get. So you can just set the temperature. So let us say like it's 80 degrees, and inputs is I want to get the back EMF at 1000 RPM. 1000 RPM. So I'll validate, I will run the model, so it will be able to run. And so that's what like we need to set up. Similarly, like I can explain you other things, like we have other setup characterization setups, like where we need to do the settings like thermal, electronics, and mechanics. And the results that we can expect from this particular test is like the fluxes and inductances, and and also like the mechanical losses and total losses we can get. Similarly, like you have all other tests, like I would like to open the solved model and explain you what are all the results that we get, so that like it will be clear. So I will try to open the solved model. Okay, so this is a solved model, and as you can see here in the cogging torque, so I have run the cogging torque, and you can see here. So first thing in the cogging torque is basically like the cogging torque. So for one slot pitch, you can see here. So this is what like will induce the torque ripple, and because of which we will get the noise in the permanent magnet machine. And on the cogging torque, we can also do the harmonic analysis and the impact of harmonics. You can see the fundamental and the second, third, and fourth component of impact. And we can also have the magnitude of the harmonics, and also like the phase and frequencies. You can see here. And then we can go to the back EMF. So in the back EMF, we will see. So we will. Okay. So we ran it at like 750 RPM. So it's okay. We can see here the results. First results we get it from the back EMF test is phase voltages. You can see it's in the sinusoidal fashion, and we can also have the phase voltage harmonic analysis, and then like we can also have the phase voltage harmonic analysis. If you want to have a magnitude of particular harmonics, you can also have that, and the phase of that particular harmonic and the frequency. Similarly, like we can also have a line to line voltages harmonic analysis, and the line to line voltage, the magnitude for a particular corresponding to the particular harmonic. And then this is the flux density in the air gap we can compute. You can see here, which is very important, and harmonic analysis of the flux density. And then we can also have a flux with respect to angular, the rotor angular position. So you can see three-phase flux. And then we can also have a saturation, which is basically like the flux density distribution. And then like we can also have the vector potential magnetic field lines, as you can see here. And then like we can also see the mesh. So so since it is a semi-analytical tool, that means like it's in the background, right behind the screens. Basically it will use a flux, which is a finite element solver in the background, to compute these kind of results. And so that's what about the open circuit test. So we will move to the the model test quickly. Like I will give you some insight about what are all the results that we can expect. So in the model test, as I said, overview, you can have a thermal, electronic, and mechanical settings, and we can give the maximum line current and speed as an input, and these are all the outputs. So let me give you some insight. So we have a d-axis flux linkages in the ID and IQ plane, so which is very important for the controlling of the motor, and we can have q-axis flux linkages in ID and IQ plane, and d-axis inductances, which is also important for the field weakening region, field weakening control technique. So if you see, it's a d-axis inductance in ID and IQ, q-axis inductance in ID and IQ, and electromagnetic torque in ID and IQ, and iron losses in ID and IQ. You can see. So we can also vary the the RPM, and you can see the what is the iron losses for a particular RPM, and on the ID and IQ plane. And then we can also get the joule losses and the total system losses. Okay, so full system losses, total losses at a different RPMs you can select, and you can see so how the losses are how the losses are there on ID and IQ plane. So this is what we can compute from the the model test. Then like we can also do the data sheet test, so from which like you can get the torque ripple, as you can see here, and then like we can also have a mechanical torque versus current versus control angle. So control angle is nothing but the angle between phase back EMF and phase current. We can also compute that, and voltages, line to line voltages, and you can see the flux density in the air gaps. So this is what we can do in the data sheet test, and then we can do the full characterization, so efficiency maps. So first thing is basically, so you can see we can compute the torque versus speed, okay, characteristics. We can also have a current versus speed, so ID and IQ currents also we can display, and then we can have voltages, so VD and VQ voltages, and then the control angle versus speed, and power versus speed, and then like power factor versus speed, and then like the losses versus speed we can compute, and then the the electromagnetic torque versus current and control angle. So we can also have a full characterization on ID and IQ plane. So that is a d-axis phase currents versus q-axis phase currents for the working point, and also for the currents and voltages, and also for the electromagnetic torque. So this kind of maps we can get. And then once we have these maps, we can also compute the efficiency. So these are the the efficiency maps, 3D graphs we can display. So this is a efficiency in the torque and speed area. Okay, so efficiency, machine efficiency versus on the speed and torque area. So torque versus speed, with respect to efficiency. And then we can have a the phase current on the speed and on the torque and speed area. So the phase current, and then similarly like we can have a phase voltages and a control angle, and you can also see like we can have a mechanical machine electrical power, and a power factor we can have for the on the speed and the torque envelope, and similarly like we can have a total machine losses. We can have iron losses and joule losses, and we can also have the mechanical losses. So that is what about the efficiency maps characterization. So once you do this electromagnetic analysis, we can also do the thermal simulation. So for the thermal simulation, what we do is like the total losses that we compute from the electromagnetic simulation will be the source of heat. So you can see here all the losses on the stator, joule losses, and stator iron losses, and also the magnet losses. So especially like eddy current losses, and then the iron losses. We try to take all those losses and we give the input, or like we give those losses as a source of heat, and we compute the thermal distribution. You can see this is the one example, the radial view, the temperature distribution, and you can see the temperatures at the different locations of the motor, and this is a axial view. Okay. So once you do the electromagnetic simulation, then we will switch to the thermal simulations. Once we do the thermal simulation, it is also possible to do the NVH simulation, so noise and vibration analysis, to estimate the noise levels. Okay, so one classical example here. So this is what like we have done at one single working point. So that means at a one control angle and one current, and also at one particular speed, I did the NVH analysis. So similarly, like you can do at several working points. and the results that I get is this is the first one: frequency versus number of lobes. It's a basic. It means that the computation of a natural frequency for each number of lobes when we consider, and then like we have a radiation efficiency, which means that the capability of a mechanical structure to observe or to filter out the vibrations. Okay, so you can see the radiation efficiency, and then we can also have the normal flux density in the air gap. So inside the air gap and the corresponding, we can also have a corresponding Maxwell pressure in the air gap. So in the space and time area, and then we can also have the Maxwell pressure. So it's basically another way of representing the Maxwell pressure. So Maxwell pressure considering the different values of angular, the position, so rotor position. So you can see here, we can do this, and then the Maxwell pressure in the space and time, the harmonic analysis. So it basically helps to see where exactly the hot points to be considered at the EM point of view. Okay, so from the EM point of view, it will help us to consider what are all the the hot points are there. So you can see this red color one. So these are the points where we will have a the impact coming from the electromagnetic point of view. And once we combine these particular results with the radiation efficiency, we will have this result, which is like radiated sound pressure. So which is basically the indication for the noise. So that is what we can compute. And so as you see here in the Altair flux motor technology, we can do the electromagnetic simulations step by step for the cogging, back EMF, for the efficiency maps, and also like to compute the the model characterization and datasheet test, and we can do the thermal test, and also like we can do the NVH analysis. So that's what for the demo, and I minimize this. So I'll pause here. So if you have any questions, or if you want, so ma'am, I'm not sure like we need to give a break or how it is, or should I continue? Hello.
Sir, are you going to continue with the second session also, or
no? Second session basically is from my colleague.
Okay, sir.
So
No,
sir,
yes, sir. Then you can continue it, because after your session there will be a break of 10 minutes, and then we'll continue the session.
No worries, ma'am. No worries.
Okay, thank you, sir.
So that's what was the demo, so which I have showed you on the tool. So once we do this, it's so we have done the electromagnetic, thermal, and also like the NVH analysis. So it's also important. As I said, for the electrical vehicle application, we need to check the performance of the machine while considering the duty cycle. So duty cycle is nothing but it is in this format. So it's a 3-dimension. So it's a values with respect to time and speed and also the torque, and you consider this, and we can check the results. So you can see all the black ones are the the duty cycle points, which is superimposed on the speed torque envelope. So this is envelope considering only the machine. Okay, so you can also consider the effect of power electronics and controls, and we can also compute. We can also compute the efficiency maps, and we can superimpose those the duty cycle points. And then we can also consider both machine and power electronics, and we can consider the complete system. So system is nothing but considering the machine and also like the power electronics, where we will have a switching losses actually. And by considering that, we can also superimpose those duty cycle points on the speed and torque and efficiency envelope, and we can check if I'm operating at that particular duty cycle point, what is the efficiency that I'm going to get, and overall for full duty cycle, what is the performance. So you can see here for the full duty cycle, mean torque and efficiency and electric power. So what is the mean electric power, torque, and also the efficiency that I am going to get. So that is also possible from the tool. So that's what So as I said, in the challenges, electrical rotating machine, the design scenario itself is completely shifting. It's not a single physics. It's not a electrical. It's a multi-physics, and where we are addressing that multi-physics, targeting the electromagnetics, that is speed, torque, and power, and then we are computing all the performance data, and then we are computing the the thermal, and then NVH, and testing it with a duty cycle. Okay, once we we will do it in the concept phase. So now like we are moving to the detail stage where we will do the finite element calculations. So the finite element calculations we basically we do with a flux, which is a finite, it's a general purpose finite element based electromagnetic and thermal simulation tools. It's completely based on the Maxwell's equation, and it can do the different type of analysis. So it can do the magnetic, electric, and thermal. So when I say this, it can also do the it can do the static analysis. So that means, as I said, like it's a general purpose tool, right? So it can do the analysis of the device in time varying, time varying magnetic field, time invariant magnetic field. If you want to do the simulations at a one particular frequency, that is also possible. And also on the top of it, we can also do the multi-physics simulation. So this is the same example that I have considered in the flux motor. So I have considered here also. See, these are the results. So I brushless, that the brushless IPM motor. So it's interior permanent magnet motor where magnets are buried inside the rotor, and the rating is, as you see, the bus voltage is 500 volts, and the peak torque and the maximum power. And first one is a cogging torque, as you can see at the bottom. So this is a from finite element calculations. We will have a similar kind of results. And then like we have a back EMF, and then like we can also compute the electromagnetic torque, and once you compute that, like we can also do some advanced simulations where like if you are targeting to to minimize the losses. So this was one of the case which we have done it for the the Toyota Prius 2004 model. So if you see for flat magnet, so if you see the flat magnet, the eddy current losses in the magnets are high. So the losses are concentrated in this region. So, and if you consider the segmented magnets, so I've segmented the magnet into in axial direction. So you can see I'm able to reduce the loss concentration in this particular area, and as you can also compare the results here. So with segmentation and without segmentation, the magnet losses. So with segmentation, the losses are coming down, and because of this, because of this, we can also improve the efficiency. So these kind of advanced simulations we can do it in a detailed stage. And then a computation of iron losses, which will help us to estimate the efficiency. So we can compute that. So iron losses, we can compute both hysteresis losses and also eddy current losses. So you can see the result. So since we modeled the periodic the periodic portion, so we need to multiply it by 8 to get the total losses, and then we can also compute a similar efficiency maps. So speed versus torque with respect to efficiency. And then reluctance torque is also very important for the permanent magnet missions, and we can compute by just making the the magnets as a air or vacuum region, and we just excite the coils, and there will be like so there will be like the no magnet torque. So the total torque that is computed on the shaft will be a reluctant torque, and you can see for the same machine I have computed the reluctance torque. And then it's also important to do the skewing, as I said. So as I said, to reduce the cogging torque or to reduce the torque ripple, we normally skew either stator slots or rotor slots. So for this machine, what I have done is like I have skewed the stator slots from 0 to 7.5 degrees, and you can see here how my torque ripple is being reduced. And so from 0 to 7.5 degrees, it has been reduced from 112 Newton meter to the 16 Newton meter. The torque is reducing, but it's manageable. And you can see like the torque ripple is it's almost like it's the torque ripple is almost reduced, and if you see the curve, it's almost flat. But yes, we have some ripples. If you can further go, if you can further increase the skewing angle, like we can have a flat line. And then so that is what on the detailed stage advanced simulations we perform, that is a finite element calculations. And till now we have spoken about the healthy operation of a machine, but it's also important to check the non-healthy operation of a machine, or failure operations of a machine. So at the design stage only, it's important to do those simulations, and you can have a certain what is a tolerance level that we can allow the current and all those things, because we need to fix the temperatures at the magnets, and also at the winding. So it's important. So what will be the impact of short circuit? We can simulate that. As you can see, once we have a short circuit, the current levels are higher, as you can see here. So this is also done for the the IPM motor, brushless IPM motor. Another one is basically like the demagnetization. So demagnetization is a very important, and we need to simulate that at the pre-design stage only, in the where we demagnetize the magnets, and we will look at like what is the performance that I am going to get when we have a demagnetization. So if you can look at this, so with and without demagnetization. So with demagnetization, the torque levels coming from the motor is being reduced when compared to with without demagnetization. And it's also important to look at like what will be the impact of eccentricity. So eccentricity is nothing but shift in the rotor axis. So as you can see in this image, the rotor axis is now shifted. So because of this shift, the air gap is not uniform. So as the air gap is not uniform, we will have impact. So we will have impact on the the torque. So that we can simulate from the flux simulation technology. So that's what for the non-healthy operation of electromagnetic simulations. Now we will move to another domain called thermal. So why we need to do the thermal? Yes, electrical rotating machines is which converts basically like there is a which converts which basically converts electrical energy into mechanical energy, which basically because of which we will have some losses, and once we have these losses, like it will be converted into the heat and thermal, which is dissipated inside the motor, because of which we will have higher we will have some temperatures of the at the magnets, and also like we have some temperatures at the windings. So the motor the magnet temperature should not exceed certain levels, because like for example, like let us consider ND-FEV magnets, like where the temperature limits can range from 150 to 180 degrees. So we should not go beyond that particular temperature. And also like for the copper the windings will have insulation, so we need to have a better insulation class, and each insulation class will have a limit on the temperature, so we need to select that particular class. So that's why the reason it's important to simulate to simulate the thermal simulations of the electrical rotating machines. So there are several ways to do the thermal simulation in our global workflow. One is a single working point. So at a one single RPM, we rotate the motor and we compute the total electromagnetic losses. So, and we export it to thermal and we get the temperature distribution. And second one is duty cycle. You can consider several duty cycle points and we can compute the average value of the losses, and we can take those losses to the thermal part and we get the temperature distribution. Third way is magnetothermal co-simulation. In the magnetothermal co-simulation, the point to be noted is in the magnetics, the materials are characterized with temperature, and these temperatures are updated from the thermal, and this loop will continue until we have convergence. Convergence is nothing but a minimum temperature distribution. So that is about the magnetothermal thermal co-simulation. And another one is advanced thermal simulation, where we have a CFD software in place, and we compute total losses from the flux electromagnetic technology, and we export those losses, and these losses are being mapped into CFD software. And here the advantage is basic, we can define the coolants and how the coolants are also flowing. If the coolants are flowing in a particular fashion, like we can also do that, and we can get the temperature distribution. And this is one the result on the same motor, and you can see here at a different temperatures. So at two different RPMs, I have a temperatures, as you can see here, coil temperature at a 1600 RPM and also like 200 RPM, and tooth, the stator tooth stator tooth, and also the magnet temperatures at a two different RPM. So one good advantage from our detailed stage, the flux, finite element technology is we can give you the hotspot. So hotspot is nothing but the highest temperature value and the lowest temperature value. So this we can do, and then like you can also, as I said, on the same motor, like we have done the we have done the thermal simulation for 4 working points, and for 4 working points we computed the losses, and we have mapped, and we can get the temperature distribution. So you can see in the graph how the temperatures are varying when we have a loss in place for 4 different working points. So these are the graphs on the housing, basically temperature on the housing and winding and also the magnet. And this is a CFD based result, as you can see in the animation. So we can have a complete housing, stator, rotor, shaft, winding, and we can also define the coolant. If you are cooling the motor with certain coolants, we can cool that, and then when we have a coolant, we can also map the losses and we can get the temperature distribution. So that's what about the basically on the temperature side. And then like it's also important to to look look at the what is the impact on of PWM signals, that is a pulse field modulation technique. So if you look at the motor is not pumped with pure sinusoidal waveform, right? So the signals that is coming from the inverter is not purely sinusoidal. It's like a PWM signal. So what is the impact on the PWM signals? We need to look at basically to estimate the iron losses. So it's you can see here. So this is the the one particular result where like I am pumping the same motor with the PWM signals, and as you can see here, so the current versus the rotor position. So you can see the effect of PWM, and also torque versus rotor position. So in a nutshell, I can say like there is an impact on the torque and also the iron losses. So with and without PWM, and torque is being reduced, and also like the iron losses has been increased. And so the increase basically like the torque is reduced by 2% and iron losses is increased by 14%, as you can see. So the PWM signals is also impacting your motor performance. So that's what about the the impact of the signals or like impact of the signals that is going into the motor. So on the iron losses and also the torque. Now we have done the complete simulation of a motor in the detailed stage, and also like we have at the concept phase we have quickly targeted the design, and now we have to integrate into the system, right? So I have designed a motor, but we need to integrate into the system. So that integration can be done by using our system system level simulation tool called Activate. Activate is a 1D simulation tool where you can model the complete system. So for example, here you can see here it's a battery, so it's a battery operated electrical vehicle, and we have a complete system in place with considering the driving cycle, and all the the motor module. So motor can be represented in several ways. It can be a lumped model. So or when I say lumped model, it's a patch model. And you can also extract the tables. You can extract the tables like speed, torque versus efficiency, or like the LD/LQ as a function of IDI and the IQ. So those tables like which I have showed in the the flux motor, you can export it and we can import directly into the Activate, and we can represent the motor for complete system level simulation. And another one is we can also do the co-simulation. Co-simulation, nothing but we can directly call the model that I have designed it in the flux motor into the Activate, and in the background flux motor will be there, it's running, and we can see the impact, what is the impact of the motor on other subsystems, and also like when we have a duty cycle in place. Okay, so you can also consider here the duty cycle, and we can see. So in the co-simulation we will have a real physics based model. Okay, so that is also possible. So that's what we can do. And so as I said, same thing like so different ways of representing the motor. And so this is a classical example, and it's a two-wheeler self-balanced scooter for the system simulation. Okay, and where we have also motors. Okay, you can see the motor designed from the motors coming from the flux software, and you can see here like the motors are completely designed in the flux simulation technology, and we have also kinematics defined in the motion solve. And we have to do the system simulation, we have Activate in place, which is linking flux and motion solve, and the complete plant model. This is called a plant model, which is done in the Evolve simulation technology. So this is this is how like the the system level simulation is being performed once you design the motors. So yeah. And it's also important to look at like the noise and vibrations in the detailed stage. And what we do is like we compute total electromagnetic forces, and these total electromagnetic forces we export it to OptiStruct, which is a structural simulation tool, and we map these electromagnetic forces in the structural simulation tool, and then we get the noise and vibration analysis. And if you look back what are all the source of the noise that is coming from the electromagnetic devices, or like the motor, there are three main sources. First one is aerodynamic noise. So why we will have aerodynamic noise is we have a stator and we have a rotor, and the rotor is rotating in the air gap. And once a rotor is rotating, we have, because of air, we will have aerodynamic noise. And another kind of noise is mainly coming from the mechanical structure. So if you look back, like motor has a shaft and a bearings, and also like it has a housing, bolts, retentions, all those things we will have. So those things, like it also makes a noise. It's called mechanical noise. So, and another noise is EM noise. EM noise, again, the source of the EM noise again divided into two things. One is because of slotting effect. So because of the slotting effect, we will have a cogging torque, and cogging torque will induce the torque ripple. So because of which we will have a noise. Another one is basically because of high frequency signals which is going into the electrical rotating machines because of PWM signals. So that is also creating the noise. So what we are trying to do here is we are trying to estimate the noise levels that are coming out from the EM source. Okay, and another sources, that is a mechanical one, and also like the aerodynamic noise. So mechanical one is a structural problem. So we can simulate in our structural simulation technology by having all those mechanical components. And aerodynamic noise is very small, so it's normally most of the literature is coming from the Toyota and other companies. So it says like 2 to 5%, which we can ignore. So that's what we can do. And so how to reduce the noise is basically like how we can reduce. So as I said, so we can adjust the the electrical excitation frequencies which is there in the the signal, and try to shape the rotor or stator so that like you can reduce the cogging torque, because of which we can we can reduce the torque ripple. And also it's good to optimize the mechanical structure of the machine, so basically to reduce the the mechanical noise. So if you can do that, like we can we can reduce the noise that is coming from the electrical rotating machines. And this is a one classical example that I'm fortunate to show. So you can see here. So this is a the hub motor. It's a BLDC hub motor, and this case study is coming from. So it's a test case, or like you can call it as a case study. So coming from Elfi. So Elfi is a company uses our simulation technology to design the hub motors. It's a BLDC hub motor which goes directly into the wheel. And they had a problem of NVH, noise problem. They have a problem of the noise, and they use our NVH workflow to reduce the noise. And as you can see here, there, so the initial design and also the final design. So where they have reduced, for a critical range of frequencies, they have reduced to 20 dB level. Okay. On the some other case studies, like the coming from BMW, so i3 and i8 electrical cars. This is basically for the designing of hybrid synchronous motor. And as you can see here, the challenges was the high frequency, high efficiency was required, and a low weight. And when we have, as I said, like when we have a power electronics, we have a lot of problems. We need to nullify those problems, and a wide range of constant power. So especially in the field weakening region. So we need to target to reach higher RPM. So that's what they were targeting. And at the end, like they also, they were also able to reduce the iron mass, absolutely to the necessary dimensions. Okay, so they were able to reduce the iron masses on the stator and rotor. And this is one more case study coming from Ether. So Ether, basically like they use flux and flux motor technology to do the duty cycle simulations, and to compute the back EMF losses and efficiency, and also to compute the noise. And this is also coming from Valio. So it's a hybrid vehicle application. And the reason why I have taken this example is it's a completely different mission. So it's an axial flux motor. So these kind of missions can also be simulated, and it's a published paper in which like they have done like different type of performance, like a no load analysis, torque optimization, low on load analysis, and also the failure analysis, like when we have a short circuit. And you can see some of the images for the saturation and also like the induction. This is a case. Basically, I want to showcase for the people who are into electrical vehicle application. It's a regenerative braking system, and in the regenerative braking system, Hello, ma'am. Do you have any doubts? I'm getting some noise. So for the courtesy of others, if you can mute, it will be great. Hello.
Yes, sir.
I'm getting some noise, ma'am. So if you can mute.
Okay, just a second.
Okay, so if you can see here, so the machine that goes into regenerative braking systems, we can simulate and we can perfectly evaluate the performance of the machine. And if you look at the machine, so initially it will be in a motoring mode when we pump the current to it. And once you cut down the current to the motor, the kinetic energy of the wheel will be converted into electrical energy and it will be stored in the batteries. Okay, so to have so to generate that energy, basically we need to have a higher RPM. So you can see the RPMs of this particular motor is 40,000 RPM, and the maximum current is more than 900 amps. And eddy current evaluation is also important because ND-FEB magnets, because of the resistivity, we have eddy current losses in the magnets. At this higher RPMs, it's also important to compute the eddy current losses, and because of which you can fix the thermal constraints at the magnets. So that these kind of systems can also be simulated perfectly. So the regenerative braking systems, which is very important, and also upcoming technology. Then finally, I take one example for the multi-physics optimization, where we club different physics and to do the optimization. So this is the case study coming from the Porsche. So we have done this particular exercise with the Porsche in collaboration with the Porsche. So here, if you look at, it is for electrical vehicle application, by the way, and it is the objective of this particular project was to maximize the power and minimize the torque ripple. And constraints were demagnetization we have to limit at the base point, followed by short circuit. And mechanical strength we need to limit, especially stresses at the flux barriers. Okay, when we have higher RPM, we have a mechanical the mechanical stresses created at the flux barriers, because of which magnets will fall down. So we need to limit that mechanical stress. And then the winding temperature, we need to limit lower than 200 degrees. And you can see on the right side the requirements. And stator was imposed, so that means the stator was fixed. We cannot change the stator, we can just change the rotor. So that is what the objective. And you can see the objective was electromagnetics. And if you look at the constraints, we have also the mechanical, right? So that's why we are saying it as a multi-physics optimization. And so from the baseline design winding configuration, we have used a flex motor to feed the winding configuration. And as you can see here, we have compared several rotor configurations, rotor A to D, and we have compared several performance parameters first. Okay, so you can look at the performance parameters, especially torque, power, base speed, and efficiency, and also the magnet weight. So I wanted to have a higher efficiency. So you can see here, so rotor B has a good efficiency when compared to rotor C and rotor D. But yes, so when you compare rotor B and rotor A, the efficiency is where the rotor A has a higher efficiency, that is 96%, when compared to rotor B, that is 95.9%. But yes, our customer recommended us to go with a rotor B, because they also need to look at the manufacturing facilities. So that's why the reason. So we went with a rotor B. And once we have this, we have created several models. Okay, we have created the several models to meet the objective and also to meet the constraints. So the objective was to maximize the the power, right? So to minimize, and also the minimize the torque ripple. So it comes from electromagnetics. And then we also have a models from the structural. And then we also have the models from the flux to play with the torque ripple. So once we have a model, so we generate the meta models, which is very analytical, and then we can do the optimization. So in this optimization case, we have varied the the rotor profile, as you can see, and especially the magnet dimensions, and we have all the models, and we do the optimization. So this is the the result from the DOE. DOE is nothing but design of experiments. It will first software will play with the parameters, and then to achieve the goal and considering the constraints. And this is the result of basically the initial design, and this was the result which comes from the software, basically to have a minimum torque ripple. And this was a design which gives me the minimum winding temperature. And this was a design which gives me the minimum stresses and the maximum torque, maximum power, and also the minimum demagnetization characteristics. So this is the result of demagnetization. And then we have optimization. So to achieve the objective by respecting the constraints. So the objective was maximum base output power, and I need to reduce the minimum, reduce the torque ripple. And you can see the initial performance. Base torque was 155 Newton meter, and torque, base torque ripple was 8.5, and that stresses was like 2600, 2316, and the winding temperature was 200 degrees, and demagnetization factor was 6.56. And you can see the constraints also on the right side. So we need to limit the stresses lower than 500 megapascal, and winding temperature I want to limit to 180 degrees, and the demagnetization should be lower than 500 degrees, 5%, and then the base torque should be greater than 150 Newton meter. And this was an optimum design after doing the optimization. One thing I want to stress, like you can see here, the base torque was 150 Newton meter, and the torque ripple was reduced. And if you look at the stress at the at the flux barriers, so it was initially it was 2316 megapascal, and then after the optimization we have 500 megapascal. So the winding temperature was limited, and the demagnetization factor was also limited. So that was a constraint. So this kind of simulations we can do with our optimization technologies called hyperstudy. So we club flux with hyperstudy to do these kind of the multi-physics optimizations, and also like to do the several multi-physics. And at the end, like we also got some surprise. So the surprise was the magnet weight was reduced by 40%, which is good, right? So as I said, at the start of my presentation, the cost of the machine is directly proportional to the cost of the magnet. So 40% saving in the magnet weight is basically huge advantage, because of which we can save some cost. And on the top of that, it's also important for the electrical vehicle, as I said. So we need to pump with the PWM signals to look at the the iron losses, as you can see here. So I pumped with the motor with PWM signals, and you can see because of the PWM signals, like the magnet losses, and also like the iron losses, and also like the iron losses on the stator and rotor, it's completely increased. And because of which, like there is a 20% higher temperature in the magnets, and also like a rotor yoke. Okay. So it's also important, and we need to check that, and to check the temperatures. So that's it on the technical side. So if you have any questions, like you can ask me. Like I have few slides to explain to tell you about the Altair University. So I'll be stopping here. Like if you have any questions, we can take up the questions. Then I can conclude it with some slides on the Altair University from the Altair. Rupesh, sir, and
sir, there is one more question in the chat box, sir. It's from Mamta Patwardhan.
Okay. Mamta Patwardhan.
Yes.
What is the meaning of thermal weight? So so I didn't tell any thermal weight. Thermal simulation you are talking about, I'm not sure. There is no meaning for thermal weight. Thermal performance, or maybe like thermal performance. Thermal basically it's for the electrical rotating machines, we have a losses, and these losses we try to take it to the thermal part, and we just try to Okay, so there is a question from just to conclude on this particular question, we have for the thermal, like we can also do the thermal simulations, and for the thermal simulation we have losses as a source of heat, and we take these losses to get the temperature distribution on the electrical rotating machines. Okay, and so there is also a question from Meena. So please explain the relative benefits of flux and ANSYS software. So it's an open forum. It's not good to compare and tell the benefits. So, but yes, like there will be a lot of benefits, and maybe like at the end of the presentation, I would like to show I would like to share my email address, so you can contact me, so that like it can give you what is the advantage. But yes, like since like this is an open forum, so it's not good to compare and tell like what are all the benefits. So, yeah. If you have any further questions.
So participants, are there any questions?
If you have any questions or if you have anything, please let us know. I will be happy to answer. If there is no questions, I can switch to the presentation to wrap up the presentation.
Sir, you can just share the mail ID so that the participants, if they are having any questions, they will contact you, sir.
Yes.
Okay, sir.
At the end of my presentation, I will be
Okay, sir.
giving the mail IDs.
So you can proceed further, sir, then, if there are no questions.
Okay. So just to conclude my session, so that basically like I would like to introduce Altair University. So Altair University is a program, is everything about the software. So it's where you can learn and certify, and we will also have a student competition. We have a sponsors, and also we will have a the technical support there. So please try to visit Altair University, so where you will have access to the free ebooks, and we will also have a student guides, and you can also download the student versions of the software where you can practice it, and also like you will have access to the research licenses and free ebooks on the electromagnetics. It can we have a lot of ebooks which is available there. You can access those ebooks. You can also learn and you can certify there. Okay, so you can also write. There is an examination, so you can, once you do the go through the the process. So you can also you need to answer certain questions where we can give you the certification. So try to visit Altair University for the certification, and you can also learn from the users. There is a forum, so where you can post your questions so that you can learn from the users. And we also have a student projects, or like the lab projects there available. So you can download those projects and you can try to do it in the on the software, and practically you can also simulate those projects. And then we also conduct the student competitions, and we also have a we also choose an ambassador. We also have an ambassador program, and also like industry outreach. So where you will have people from the different different walks of life, and it so where like we will also have expertise where they can comment. So you can also do the networking and also like get the suggestion from them. And so that is what about the Altair University. So I would encourage you to visit the Altair University to make a utilization of these particular facilities. And we also have a lot of webinars. So basically, like in this session, I have concentrated on especially on the motors. But yes, like if you are interested in any kind of low frequency electromagnetic technology, like generators, or like or like the actuators, or like the circuit breakers, or like if you want to do the electric field calculations or induction heating, I would encourage you to visit our website, where like you have a resource library where there are a lot of webinars available, and free academic versions for Flux is also available, and the learning certification programs are also available. So I would encourage you to visit. And there is also moderate support forums available where you can ask your question, so that like we will answer it. And I just recommend you like just to scan this QR code, so that you will have access to all these particular the facilities or ebooks, the application notes. So yes. And so I think like if you have further questions, you can ask me, and or like you can also post the questions. Here is email addresses. You can post to anybody of us. We will be able to happy to answer the questions.
Sir, there is one more question in the chat box also, sir.
Okay. So, okay, let me. Software is good. It is well explained. Thanks for making the student versions available. Hands-on practices would have made more useful. It is good presentation. So it's just a comment.
One more above, sir. One more above that.
It is.
From
Is
the
it possible?
electrical.
Yeah. So is it possible to analyze the performance of switch reluctance motor in Altair software? Yes, we can do that. Yes, we can do that. We can do the switch reluctance machine simulations. Yes. So as an example, I have taken permanent magnet machines, but yes, we can do the switch reluctance motor. Yeah, if you have some more questions, I will be waiting for 2 minutes.
So participants, if you have do questions, otherwise you can mail your questions on the mail ID whichever sir has displayed on the last screen.
So maybe I can put.
Yes, sir. So you can have your queries on the mail IDs. Okay, sir, we will conclude here because we'll having the second section again. So
Yes.
if the participants have any questions, they will contact you on about to mail IDs also, sir.
Yeah.
So I,
Thank you.
Sharmila Chogle, would like to conclude today's session, which was conducted by Mr. Sandeep Ramagiri. It was a very delightful session, sir. And he has also discussed about the Altair software technology, the different simulators which will be used, and discussing about the different applications where we can use these simulators. He also highlighted about the challenges in traction motor design and typical specifications, analytical computation and motor topology selection. Guidelines about how to use number of poles and slots, rotor, designing of electrical motors. Sir has also covered how to simulate by choosing different parameters. System integration by using Altair activity. So it was a very informative session, sir, and I consider that all the participants have got an idea of using Altair software. So thank you, sir, from behalf of Department of Electrical Engineering, Modern College of Engineering. Thank you, sir. Thank you very much.
Thank you very much. Thank you very much for attending this session. I hope the session was useful, and thank you very much for inviting me. Once again, I would like to thank Modern College of Engineering for inviting me. Thank you.
Thank you, sir. Thank you. The second session will be starting from 12 o'clock, and it will be covered by Mr. Rushikesh Shirkis.